This is the lecturette for section 12.3 involving the structure and properties of ionic solids. What we'll be looking at is ionic solid unit cells and formulas, how we describe those in terms of unit cells of anions with holes inside which cations reside, and we'll look at some important unit cells, and then we'll talk about what controls the shape. Why do particular salts take the shapes they do, the unit cell structures they do, and we'll finish up with some calculations you can do related to the unit cells of ionic solids. So we'll first start talking about unit cells and the formulas of the ionic compounds that adopt them. And this is similar to what one would do with just the unit cells of metals, but now there are two different elements involved. So here we're just going to do one where we have a prototypical metal, M, or X, a prototypical metal So here we're going to do one where we have a prototypical metal, M, and that'll be our small sphere, because metals make cations, which are small, and a prototypical anion, X, where X is the anion and it's large. And so if we look at this particular unit cell, the anions make a unit cell that is a body-centered cube, and that body-centered cube has 8 corner atoms, and inside that unit cell, 1/8 of each is inside the unit cell, so that's 1, and 1's inside the unit cell, so that's times 1. So there are a total of 2 X atoms, or in this case they'd be ions. For the metal, what we have is we have 4 inside, and so the unit cell structure for this structure is going to be M4X2. Next what we'll do is look at another one. This is actually the structure of an oxide of cesium. Cesium are these atoms on the corners. The oxide are the edges, the gray ones here. So if you look at it, the cesium has 8 atoms on the corners and 1 atom inside. So the cesium has 8 corner atoms. Those are 1/8 each, so that's 1 cesium. 1 inside. That's this one right there. That equals another cesium. So there's a total of 2 cesium atoms. The oxygens, the oxide ions, there are 2 inside, there and there. So those are fully inside there. So that's 2 oxygens. But then there are 8. That is 4 pairs of oxygens. So there's 8 on the edges. So there's 8 edges, and those are 1/4 inside the unit cell each. So that's a total of 2 more oxygens. So it's a total of 4 oxygens. So the formula of our unit cell is CS2O4. Okay, so that's how you do this. So it's similar to what we did for metals. Now what we're going to do is we're going to talk about ionic solid structures, unit cell structures, in terms of a way of describing them where we admit to ourselves that the anions generally are much larger than the cations. And so what we do is we take our set of anions and think about the unit cell being the shape the anions take. And so this is the unit cell for cesium chloride, which we'll see in a little more detail in a bit. But the cesiums make a shape, and we talk about the unit cell being that shape, but then inside that shape, in the cavity there, better seen here, the cations fit inside that cavity. And so here's a unit cell. This is the unit cell for a part of the unit cell for sodium chloride. And so these are chloride ions. So we think of the unit cell of chloride ions, so that's a face-centered cube. And if you start taking away atoms, take these ones away, kind of clean up a bit, you can see there's a sodium inside there. So the sodium's inside that cavity in there. And so what we do is we think of the metal ions as being inside cavities called holes inside the unit cell, which is composed of the anions, making the framework. So we'll go through the 3 major kinds of holes we have. When you have a simple cube of anions, the hole inside of which is called a cubic hole. So in the case of cesium chloride, the cesium ion, is inside a cubic hole of chloride ions. The other thing that's important here is that the cesium has what's called a coordination number equal to 8. And that means it has 8 nearest neighbors of chloride ions. The cesium is abutting or touching 8 different chloride ions. So two other kinds of holes are tetrahedral holes and octahedral holes. So a tetrahedral hole, you can envision if you take three balls, tennis balls, apples, anything that's round, lay them down, and put another ball on top, there's a cavity right there. And that cavity is called a tetrahedral hole because it's bonded and would be attached to four different atoms around it in a tetrahedral geometry. If you take those same three atoms on the bottom and add another three on top but twist it around, you would have one here, and that's called an octahedral hole because it's now bonded to six different things, and those things are along the Cartesian coordinates, x, y, and z coordinates. We'll see more examples of these as we go along. So let's look at another way of visualizing this. Here we have a unit cell of anions. The anions are the more lightly colored spheres, and the cations are in the more darkly colored spheres. And what we have is the anions, that is these, make a face-centered cubic lattice. And if we look at this atom here in the middle, it sits in a hole inside the anions. And if you think about what it's attached to, it's attached there, 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 and there. And that's an octahedral geometry, that just same as what we had for looking at molecular structures. And so here's a view of that with the kind of lines attached. And so this atom here sits in an octahedral hole, the same one as that. And it has a coordination number of 6, because it has 6 nearest neighbors of ions of the opposite charge. In this case, we have the same, if you examine these two structures, we have the same unit cell structure for the anions, the things on the outside, or for the outside atoms. And so it's a face-centered cubic unit cell of the outside ions. And then these ions here are in what we would call tetrahedral geometry. So if you look at this, 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 and this, it's bonded to 4 different things, and that's the shape of a tetrahedron. So these are tetrahedral holes, and they have a coordination number of only 4. Okay, now we're just going to review some of the 3 of the most important unit cell types for ionic compounds. The first is cesium chloride. Here's an extended view of a cesium chloride unit cell, of cesium chloride solid. And if we take the unit cell, which is essentially that box there, made into a cube, what we have is we have a simple cube, or primitive cube is another way of saying it, of chloride ions. And inside the middle of that is the cesium ion. In the same picture we saw before, the cesium is there with a coordination number of 8. This is the one unit cell where it's an A unit cell where the cations and anions can be thought of to switch positions, and it makes no difference. So here we can have a simple cube of chlorides with the cesium occupying the hole in the middle, or you can have a simple cube of cesium with the chloride occupying a hole in the middle. If you look at this structure, you can envision both of those happening. This unit cell happens when, that is, it's adopted when the size, the radius of the cation, is about equal to the radius of the anion. And that's because it can do this switching thing, or it can do the switching thing because of that. So when you have a relatively large cation and a relatively small anion, they'll be roughly the same size, and you get that kind of structure. This is the sodium chloride unit cell, and this is an extended version of it, more than the unit cell is the sodium chloride structure, and it has alternating positive and negative ions in each direction, x, y, and z. If you look at a particular ion, we're going to look at this one right here, up there. It shows that that's a sodium ion. It shows it has it sits in an octahedral hole. Octahedral hole, and it's 6 coordinate. You can also look at the anion, that is, we're going to look at this anion right here now, and the chloride ion is also 6 coordinate, meaning it's essentially in close proximity to 6 sodiums surrounding it. Another view of this is that we can look at kind of the ball and stick model. We can look at what the size of the actual atoms are. And an important thing about the sodium chloride unit cell is that the ions that touch each other go along the edges. So those are in direct contact. So that edge length is related to the radii of the anions and the cation. But if you go across the unit cell, there are gaps. and you can't measure those gap. You can't assume that those gaps are 0. If you look at the internal features of the unit cell, that is, you cut the unit cell along its boundaries so that these are just the things that are inside, what we see is that the anions, let's say chloride, there are 8 corners, so that equals 1 chloride ion, and 6 faces, that's like this and this and this, and 3 on the other side. So that's another 3 chlorides, so it's a total of 4 chlorides. And then the sodiums, there's 1 inside, hard to see, but it's right in there. And then there are 12 along the edges. So those also add up to 4 sodiums. So one unit cell has the formula Na4Cl4. The last of the important unit cell types is zinc blende, and zinc blende is a version of zinc sulfide. And so here what we have is we have a face-centered cube of sulfur, and we have 4, and so the sulfur has 4 sulfur atoms total, or ions either way. That is 6 on the faces, 8 on the corners, same as we've done a few times now. And then there are 4 zinc ions inside. So the formula again is zinc 4, sulfur 4. But notice here that what we have is, in this case, the coordination number for the cation, the zinc, is equal to 4. When we did the coordination number for our sodium here, that equaled 6. And when we did our coordination number for cesium chloride, it was 8. Okay, so let's review this for a second. The idea is that when you review and compare, say, the 2 lattices for, say, NaCl and zinc blende, the key is that the anions are forming the same unit cell structure, but the cations occupy different holes. But end up with the same formula overall. Now let's look at an interesting example of 2 unit cells that are very similar. Both have a face-centered cube portion of the thing, and they have atoms in tetrahedral holes. The difference here is that this one has 4 internal atoms, but this one, notice, has 8 internal atoms. So this unit cell will have the formula something on the order of M4X4. That is a salt for which there are 4 metal atoms and 4 anions. This one will have the formula something on the order of, if we count the big atoms on the outside as the anions, we could have M8X4. And so these 2 cannot be interchanged for the same kind of compound because they have different kinds of salt types. So this is from a 1-to-1 salt, meaning the same number of cations and anions, and this is for a 1-to-2 salt, where there's twice as many either of the cation or of the anion. So these are different crystal structures with the same kind of sites, but different numbers of ions occupying those sites. So let's talk briefly about why it is that different solids take different crystal structures. So notice each of these is a 1-to-1 crystal structure, meaning that there's 1 cation for each anion when you do the formulas for each of these. And so, for example, cesium chloride will take this shape, sodium chloride will take this shape, and zinc sulfide will take this shape. Why is it that they take different shapes? Why don't they all just take the same shape? And the answer lies in the fact that stability comes from the ability of ions to be near each other. The more close contact between ions, the more stable the ionic bonds. And so what happens is the most stable arrangement is where you get the most coordination number, the greatest coordination number, the biggest number of close attractions, without leaving any gaps. If you leave gaps like we see here, that's bad. If you get high coordination number, that equals good because you get more cation anion attractions. So what happens is you have the greatest coordination number, that means going in this direction, as long as you don't leave gaps between the cations and the anions. That is, the cation fits snugly in the hole between the anions. And so generally what happens is as the ratio of the anion to the cation increases, the coordination number decreases. So you get this kind of thing with really small cations, because the hole is smaller, and you get this when you have relatively large cations, assuming similar anions. Okay, finally, let's look at a couple of examples of things you can calculate involving unit cell dimensions of ionic compounds. The first is if you measure, which you can do experimentally, the radius of a particular atom or the unit cell dimensions. If you know the unit cell dimension here of this unit cell, which is of magnesium oxide, what we have is we have an oxide here, a magnesium 2+ here, and an oxide there. The idea is you can measure this using Bragg's law to be 420 picometers. That's equal to the radius of the oxygen here, and 2 times the radius of the magnesium. So the 420 picometers is equal to 2 times the radius of the oxygen 2- plus 2 times the radius of the magnesium 2+. So that's equal to 2 times the oxide ion, which we are saying we already know to be 126 picometers. So 420 picometers equals that, plus 2 times the radius of the magnesium. And then we can solve for the radius of magnesium, 2+, to be 84 picometers. Okay. Next, let's say we have this cadmium fluoride crystal, and it takes the same shape as what would be called the calcium fluoride structure, but it's actually a cadmium. And what we want to do is we want to calculate the density of cadmium fluoride in grams per centimeter cubed. And all we know is we know what kind of crystal shape it takes, that one there, and we know that that edge length is 540 picometers. So the density is going to equal the number of grams, the mass in grams, over the volume in centimeters cubed. And so what we're going to do is we're going to get the volume by cubing the edge length. So 540 picometers is 5.40 times 10 to the minus 8th centimeters. So if we cube that, what we get is 1.575 times 10 to the minus 22 centimeters cubed. Then what we need to do is so that's the volume of a unit cell. We need to figure out the mass of the unit cell. And to do that, what we need to do is we need to figure out how many cadmium fluoride units there are in our unit cell. So in our unit cell, the cadmiums are adopting these positions because we know that there's 4 atoms in these positions and 8 in the other ones, and we need more fluorides. So the fluorides taking those. So we have a total of 4 cadmiums plus 8 fluorides. So that means we have 4 cadmium fluorides. So what we're going to do is we're going to take 4 cadmium fluorides times 1 mole of cadmium fluoride for every 6.022 times 10 to the 23rd units. A unit's like a molecule, but we're talking about ionic compounds. And then we're going to multiply that by the molar mass of cadmium fluoride. What is the molar mass of cadmium fluoride? It is 150.4 grams per mole. And so when we do that out, we get 150.4 9.99 times 10 to the minus 22 grams. So therefore, the density is equal to 9.99 times 10 to the minus 22 grams divided by 1.575 times 10 to the minus 22 centimeters cubed, and that is 6.36 grams per centimeter cubed. And that is that.